Welcome guys! Today we're going to be solving an Olympiad geometry problem using a very quick and efficient method. So, we're given an isosceles triangle, ABC, with the length of its altitude to its base being 3, and the base itself being 8. And we have to find the length of the altitude to its leg, CE, right here. So at first this problem may seem pretty challenging because unlike angle bisectors and medians in triangles, altitudes don't really have that many unique properties, except that they give us very useful right triangles. And where there are right triangles, there may be a chance we can apply some trigonometry. So that's exactly what I'm going to try to do here. Okay, so first it's to use some trigonometric ratios. It's better to find the lengths of all the segments outside triangle ABC. So let's do that first. Recall that BO, which is the altitude in here, to its base, is also the median and the angle bisector in an isosceles triangle. So we know that AO is equal to OC, and angle ABO is equal to angle OBC. And from that, if AO is equal to OC and we know the length AC, we can say that AO is going to be half of AC. AC is 8. Therefore, AO, which is equal to OC, is equal to half of 8, so 4. Very nice. Let's label that here. Both of these are 4. And with that, using Pythagorean theorem, we can also find the length of the side AB, right? AB squared is equal to, it's a right triangle, so AO squared plus BO squared. 4 squared, BO, which is 3 squared. Very famous Pythagorean triple. AB is 5. How nice. Which is equal to BC, also 5. Alright. So, to continue to make this easier, let's call angle ABO alpha, and the thing we're trying to find, which is CE, the altitude, 2x. And you'll see something pretty cool in a moment. So let's consider the trigonometric ratios of alpha here. This is angle alpha right here. So the sine of alpha will be 4/5, right? Opposite to hypotenuse. And the cosine of alpha will be 3/5, which is BO to AB, adjacent to hypotenuse, 3/5. Very nice. But what can we do with this later? Remember that CE is an altitude. It forms its own right triangle, BEC. And alpha is very close to being part of its angles. And if we again remember that BO is an angle bisector, we know that angle ABO is equal to angle OBC. These are both alpha. And together they are 2 alpha. And 2 alpha is an angle in triangle BEC. Very cool. That means the sine of 2 alpha will be EC over BC. And we know BC. It's 5. Sine of 2 alpha is equal to EC, which is CE, which we call x, over 5. And one last thing, we're almost done here. What is the sine of 2 alpha? It's a double angle identity. You have to remember that. And it's going to be equal to 2 sine of alpha times cosine of alpha. And look at this magic. We have sine of alpha and cosine of alpha known to us. How nice is that? And by transitive property, we can just set both of these equal, and we will get x over 5 equals to 2 times sine over alpha, which is 4/5 we have from above, times cosine of alpha, which is 3/5. And that's it. Just solving this simple linear equation will give us x, which is the thing we need to find. And yeah, that's basically the solution. Let's solve it real quick. X over 5 is equal to 4 times 3, that's 12, times 2 is 24, over 25. That means 25x seems like 120 Therefore, x is going to be 120 over 25, which is just 24 over 5. And that is our final answer. CE, the altitude to the triangle's legs, is 24 over 5. Then that is it. A very nice solution. You can consider this when you see altitudes next time in the problem, if they form right triangles, if you have the lengths. Just remember some trigonometric identities, and it shouldn't be that hard. Thank you for watching.